Myself, I am Dr. Jntuh. In this class, we are going to discuss with the deadlock avoidance situation. Before moving to the class, we should know what is a deadlock avoidance. So, deadlock avoidance is a situation in which a system is going to be require some of the additional informations depending upon the requirement of how many number of resources are there. In this case, the more number of resources is available there, we have to make use of the particular resources in an effective manner. So the best solution for avoiding this lack of resources is the deadlock avoidance procedure. Here we can dynamically share the resources to ensure that all will be waiting in never in a circular queue. Like that, we should ensure that particular condition. Depending upon the number of resources, the state should be transferred and the maximum number of processes will be available for the particular process will be shared the equal number of resources there. In this, there are two state conditions are there. One is a safe state and another one is an unsafe state. Safe state is nothing but whenever a system allocate the resources to each and every process in some order, the condition of deadlock will be avoided here. When a process is making a request to the particular available resource, the system must decide and immediately allocate the particular system the resources. That condition is called as a safe state. In the sequence of process, P1, P2, and Pn, the safe sequence for the current allocation that each resource for the process P1 that should have a resource of R1, P2 should have a resource from R2, and Pn should have a resource from Rn. Like that, they have to share the each resources and should be not enter into the deadlock condition that is called as a safe state. Here, example has been given. For example, the P0, P1, and P2 have the maximum need of 10, 4, 9, and the current need is 5, 2, 2. Like this, for the process P0 requires the 10 number of resources. P1 needs another 5 resources. P2 is having the 4 resources. P2 is having 9 resources, and P1 is having the 4 resources. Like that, each will be holding such of a resources. It should satisfy the condition of the particular process and wait for the other process to allocate the rest of the resources to. So this condition is called as a safe state. Moving to the next condition, it is unsafe state. Here, the more number of processes will be available, the limited number of resources will be available. If in this case, this deadlock situation will occur. For example, for 2 number of processes are there and only 1 resources is there, the resources is either may be allocated to P1 or to P2. In this condition, the system will enter to the unsafe condition. The deadlock situation may occur. The resources either may share to P1 or shared to P2. So this condition is called as unsafe condition. In this condition, definitely deadlock will occur. For a single number of resources, a resource allocation technique is used. For the multiple number of resources, we can use the Banger's algorithm for the deadlock avoidance procedure. Here, this can be explained with the help of this graph. Resource allocation graph is a single instant of deadlock avoidance. Here, the resources must be claimed in prior to the system. Here, no cycles will be allocated. If a cycle is formed, then the system is purely set to the unsafe condition. Whenever the request made to the request from the P2 to R1, here the request edge is made and the assignment edge is done with the resource R1 to P1. Hence, the resource that is allocated for the P1 only from R1, not from R2. Hence, this edge is called as a prime edge, this edge is called as a requested edge, and this edge is called as a assignment edge. Moving to the next one. Suppose your process P1 is making a request to the resource. The request is granted only for converting the values. Other will not be at the resource. Means they should currently feed the particular process and enters the unsafe state will be moved to the safe state and share the resources. So this is the only solution for avoiding the resource allocation graph problem. So the next deadlock procedure, avoidance procedure is Banger's algorithm. Here, the banker's algorithm determines whether the particular allocation of resources will be in a safe state or not. Each time, the condition has to be checked with the available number of resources. Whenever the process refers to a particular resource, it must have a wait state to occur. Whenever the process get all its resources, it must return the resources to the certain amount of time. It can be explained with the different criteria: available, max, allocation, and need. Available is nothing but how many number of available resources used for each time by the process. Maximum defines how many number of maximum demand of the process is needed by the instances that like that. Allocation is nothing but the resource is going to be allocated, how many number of resources at each instant. Need is nothing but each time the process will need some amount of resources and instances. How it are combined is called as a need. So the next procedure for checking the banker's algorithm is, first of all, the workers allocated will be having an index value that is called as work is equal to available. Whenever the value is going to be filled, when the condition is going to execute that particular condition is true, it will proceed the resources and instances. Otherwise, if the condition has become false, it will go to the unsafe state. If the work is going to be allocated in a manner and the resources effectively allocated to the particular system, then the condition becomes true. The system will be in a safe state. Otherwise, the condition becomes false. It will went to the unsafe state. If the available resources, find out the available resources. The formula is available minus how many number of requests that have been made by the particular resources. For the allocation, the formula is allocation number of resources plus how many number of requested resources are there. To find out the need matrix, so need minus number of requests. Suppose consider this problem. Here the problem is 5 processes are there: P1, P0, P1, P2, P3, and P4. 5 processes are there. Each will be having the different types of resources R1 and R2 and R3. It having instances of 10 instances, 5 instances, and 7 instances. Here from this graph, this is a snapshot for the particular algorithm, allocation of graph and maximum. First, we have to find whether the need matrix of the particular algorithm. For this, the need formula is need matrix is equal to maximum allocation, maximum minus allocation. Here for the process P0, the maximum value for A is 7, and 7 minus 0, the value becomes 7 here. After that, for the B, the value is 5 here, 5 minus 1, the value is 4. After that, 3 minus 0, the value is 3. Coming to the process P1, the value of 3, here A is 3, 3 minus 2, the value is 1. 2 minus 0, the value is 2. 2 minus 0, again the value is 2. For the process P2, the value, maximum value is 9. 9 minus 3, the value is 6. 0 minus 0, the value is 0. And 2 minus 2, the value is 0. After that, for the process P3, 2 minus 2, the value is 0. 2 minus 1, the value is 1. And 2 minus 1, the value is 1. For the process P4, 4 here, the value of A, 4 minus 0, 4. 3 minus 0, 3. 3 minus 2, the value is 1. So this is how we have to find the need matrix. After that, we have to find out the safe sequence for each and every matrix. How we have to find means we have to check for the condition, that is need value should be lesser than or equal to the available value. Here the given need value for the processor P0 is 743. This should be less than or equal to the need value. For example, if we consider for the process P0, here the need value is 743. So this should be checked with the particular available condition 230. Whether the 7 is lesser than or equal to 2, no, the condition becomes false here. Hence, we have to check for each and every terminology. All the conditions should be true, then the process will allocate the resource to the particular one. Otherwise, it will terminate from the particular process. For example, P1, P0 is not having the condition of becoming true. All the condition will become false because all will be having a higher value. For the process P1, here the value was 0 to 0. this will be lesser than or equal to 230. In that case, all the conditions are become true. For example, 0 is less than 2, and 2 is also less than 3, and 0 is less than 0. So, for example, here we can take this into account and we can do the particular operation. That system will be go to the safe state. Here, the resources which is used for the particular graph will be moved to the next location. Even though the Banker's algorithm has several advantages, so the time of processing in this algorithm is maximum time it takes. So algorithm does not have a fixed time period. So these are the disadvantages of the Banker's algorithm. So the next approach is the deadlock detection. Unlike the deadlock prevention and avoidance method, deadlock detection is also another important method. Here we are using wait for graph, resource allocation graph, and the Banker's algorithm for using this approach. In the resource, for the single instances of resources, we are using this approach. For the edge from PI to PJ, this wait for graph has been used. So this is an example of the resource allocation graph. Here we are using the different number of resources. The cycle exists between the P1 to R1, R1 to P2, P1 to P2, like this. The second cycle is P2 to R5. After that, R5 to P4, like that. P4 to P2, after that P2 to P4. So this is a corresponding resource allocation graph for the particular single of instance. So this is for a wait for graph. Here the process P1 is shared with P2, after that P2 to P3, after that P4 is shared with the multiple processor, that is P3 to P4, after that it will look towards the P1. Here the P2 is sharing the resources to the P5. Likewise, a single instances can be created with using this available number of resources. In this, there are three conditions are there. Available is nothing but it indicates the how many number of available resources are there in the system. Allocation is nothing but how many number of resources that are currently being allocated to the particular process, and request is that each process is having a request to the particular resources and depending upon the instances. So the next topic is detection algorithm. In the detection algorithm is also similar to the Banker's algorithm. Here we are going to detect whether the particular condition is going to be allocated and the resources full. We will allocate the resources true. Otherwise, the condition has become false. The system will move to the safe state when the condition has become true. Otherwise, the system will move to the unsafe condition. Consider this diagram. So this is a problem. Here the 5 processor and 3 instances are used. This is allocation table and request and available resources in the given question. Here we have to find out the need matrix for the particular request. How we can find the resources by using the how many number of available resources can be used from the request that has been made, that we can calculate, and by moving the sequence we can calculate that particular scenario from the available number of resources. So this is how the detection algorithm is going to be work. Here the allocated value will be this and the request value will be this. So we will take this value into consideration and do the particular process. For example, the new request value which has been generated here will be applied here. Here the value of process P2 only change because the availability value all will denotes as same for both P0 and P2. In that case, one has to change the process time at this sequence, hence the value will be changed, hence the safe will be moved to the safe state. In the process recovery of the deadlock, we will having another process that is called as a process termination. Process termination is nothing but exit from the process, that we are going to abort the process from all the deadlock processes. It means that the process is going to be get out of the particular situation in which case they are running, that is called as process termination. In another condition is that is
resource preemption. Resource preemption is nothing but a rollback condition. If we preempt a resource from a process, we should roll back from that particular state. That condition is called as a rollback condition. After that, starvation condition will occur. Same process will be always used for any type of condition. In that case, the rollback condition is another important concept. Here, the cost factor which we used is taken as a victim, and it can be picked by any number of resources. In some cases, starvation of resources may occur. For example, resources R1, R2 are there, three processes are there, P1, P2, P3. The resources 2 will be shared by the three processes. Here, the starvation may occur. Thank you.